All right, everybody. When we presented our pig example lecture, I ran into a few little hiccups in my presentation, so I made this video just to clarify some things for you guys. So we will go over the same example that we did in class um, about pig and a specific example of its use and how we use its queries and the syntax behind how it all kind of works. So let's just jump right into it and get going. So our sample problem has a giant database of patents, and we are interested in finding patents that are often cited together. Okay, so how this works is there is a patent, and on the very bottom of it, it cites a whole list of other patents. Okay, so we're interested in patents that are cited together. This kind of tells us that they are similar to each other. So we're looking for similarity in patents that are cited together. Now, the first approach that is also very slow would be doing nested for loops to build all the citation pairs. So let's say you have patents 1, 2, 3, 4, and 5. You start with patent 1, and then you look at all the other ones and see where that one is cited. Then you go to patent 2, and you look at all the other ones and see where it's cited. As you can see in the third bullet point here, that would be a p-squared algorithm, the number of patents squared, which is obviously not very good. So what we are planning on doing using Pig and using distributed computing is we are making a P times C algorithm. So the number of patents times the number of citations. We should only have to go through the patents one time and to be able to find all the patents that are cited together. We will generate all pairwise combinations of the list and record each pair. Now, don't worry if that sounds confusing. We will go into all of this in the next couple slides, and you'll see this all in action in just a second. So here's the problem for you to visualize. From the first bullet point, you have patent 1. That patent cites patents 2, 3, and 4. You have patent 2. That one only cites patent 3. Patent 3 cites 1, 2, and 3, and so on and so forth. As you can see, we could also write this as pairs of tuples of patents that are cited together. So if you look at the first bullet point, patents 2, 3, and 4 are cited together. So we can create tuples out of that where patent 2 and 3 are cited together, patent 2 and 4 are cited together, and patents 3 and 4 are cited together. We can kind of break that problem up like that. And as we know, applications like MapReduce and other distributed computing applications run on these key value pairs. So breaking it up like that will be very helpful for us in processing these things. So once again, we broke our data down into these groups of tuples of patents that are cited together, and we are interested in ones that are similar. Just to reiterate, if patents are cited together, that means they are similar to each other, and that's what we're looking for. So in the output here, we counted 3 instances of patents 2 and 3 being cited together that we would say that is similar, and that's the result that we're looking for. So the first step in any Pig application is loading in whatever data that we will be working with. So in this first step, we're creating a new table and labeling it cite. After that, we are using the load keyword, and we're passing in the location of, in this case, the text file that we will be parsing and working with. After the name, we have using Pig storage, which is the storage system in Pig. We tell it how the text file is delimited. In this case, that's with a comma. And then this at the end here, we have as citing type int, comma cited type int. What this tells Pig storage is that in this cite table, we will have 2 attributes or two columns, one called citing, that will be a type integer, which will be the citing patent, and a cited column, which will be the patent that is cited. And that is how the Pig application will populate the columns using the input text file. Also notice that because the original text file came to us this way, we already have the information formatted as these tuples of citing patents and cited patents. So if you look at the top table, we have patent number 54 that is citing patent number 95. Then we have 54 again, citing 34. And so you have these duplicates like so. In the next step, we will use the group operation to create a new table. We're calling it cite underscore grouped. And we will group the previous table that we made by the citing column. So now we will no longer have any duplicates. Instead, we will have one instance of each citing patent, and in this new column, we will have a bag of tuples inside of it. So think of it, they call it a bag of tuples. You can think of it as an array of tuples of every patent that is cited by the group patent. Also notice in this example that in the bag of tuples that we have, it is always the citing patent, comma, the cited patent. And you have pairs of these. So you have the citing patent getting duplicated across all of the tuples. And in the next step, we will look at how to process this data and remove those duplicates. So in step 3, we are starting to take advantage of some of the more robust features in Pig for sorting data and manipulating data. Up till now, those familiar with MySQL or SQL Server will see that pretty much all of the queries look very similar to what you'd be using in SQL Server. So in this step, we are creating yet again a new table. We are calling it cite group double, and we are using for each, which is essentially like a for loop inside of Pig. And what we will be doing is for each entry in the previous table that we have, cite grouped, we will generate a new table where we have a group column, which is the previous table was grouped by the citing patent, and this one will just remain the same. We will generate that attribute. Then we will generate two more attributes titled cited1 and cited2. Those are the two rightmost columns. And those ones will be populated, as you can see in the query. Cite.cited will go into column 1, and cite.cited will also go into column 2. So cited1 and cited2 will be the exact same data. We are doing this, and you can see in the second bullet point, we are doing this in order for us to compute a cross product in the next step. And you'll see what that means in step 4. So in this step, in order to generate the cross product for each citation pair, we will create a new table called cocite, and we will do a for loop where for each entry in the previous table, which is cite group double, we will generate two columns. We will have cited1 and cited2. You can see in the first bullet point here, we generate those two columns by using the flatten command on the previous columns in the previous table. What flatten does is, before we had lists of tuples in the previous table, that flattens it out into a list of individual patent numbers. So those tuples get broken apart, essentially into one uniform list. If you're familiar with flat map, that is similar in functionality to how flat map works. And this generates us this cross product of each cited pair, which is basically all combinations of patents that are cited together. Um, Also note here that you do have these self-referencing pairs. So you have patent 95 citing itself, you have patent 34 citing itself, and you also have the same patents citing each other in reverse order. So you have 95 citing 34, you have another separate entry for 34 citing 95. So like we talked about, the cross product is a very big list, and it also contains many citations that we don't necessarily need. And this slide is sort of alluding to how we can possibly filter some of those unneeded citations out. For example, when two patents are similar, we could filter out entries based on equivalency of two columns, and we could also eliminate columns where the number of the first patent is smaller than the number of the second. Because if you have 2 citing 3 and you have 3 citing 2, we're trying to get rid of one of those, we could simply sort by forcing the first number to be bigger than the second, and that would get rid of one of those entries. So this would be the actual command that we would use to do that filtering. First filtering out where we have duplicates in both of the columns. We'll create a new table called cosite filtered, and we will filter the previous table that we made by the following condition, where the attribute cited 1 is not equal to the attribute cited 2. This eliminates those pairs, and this is the table that we're left with. As you can see, that eliminates those duplicates, and in the next step, we will create another table where we group the previous one by both of the previous columns. That is both cited 1 and cited 2. As you can see here, that turns into the keys that are entries in this table, and on the right, the values for those keys are all of the occurrences of them in the previous table. In this particular example, you only have, our bag only has one occurrence of each one, because in the previous table there was only one entry for each pair. But this doesn't necessarily always have to be a single tuple, as in this example. If you had multiple entries for the same patents getting cited, the second attribute here on this table, which is cosite filtered, would have the same tuple getting cited multiple times in that bag. Okay? So what this means is that in the group attribute, we have a group of patents that are cited together, and in the cosite filtered attribute on the right, we have every occurrence of that cited pair of patents. In step 7, for this step, we will just take that table and we'll create a new one out of it, where for each of those entries of patents being cited together, we will count the number of entries in that bag of tuples, where that represents the number of times each of them got cited together. And we will call that this new column that is CNT for count. That generates this table where we have patents cited together and the number of times that they were cited together from the previous table. To generate our final table, we can create this cosite flat table by taking each record in the previous one and flattening its group attribute. What that does is it takes those tuples that represent two patents that are cited together, and it simply breaks that up from a single attribute into two attributes. You can see in this table, you see the two columns representing the patent numbers, and the rightmost column representing the count of those respective tuples. So This essentially gives us our data. We have a relation that says patent 1 is co-cited with patent 2 k number of times, and that represents the 3 columns in our table. If we wanted to take this one step further and find the patents that are most often cited together, we could also do that. What this would take is just a few more steps using the same tools that we've been using. We make a new table where we're grouping the previous one by the cited one attribute. So we're grouping the previous table by one of the patents that is cited together. You could see this generates a group attribute of unique patent numbers. And on the right, we have a bag containing all of the columns in the previous table. So in the first entry, we have patent 66. And on the right, we have, from the previous table, patent 66 getting cited with patent 81, and the 1 represents the count for that citation. From this table, we can then go into that rightmost column and simply remove that first patent that we initially pulled out and made into its own group. That would just be a for each loop, and for each entry in the previous table, we would just generate a new group attribute, which stays the same, but for now the second cosite flat column, we can use the dot operator to extract only the last 2 fields from the previous column. The key is now the patent, and the value is a bag of patents and their citation frequency. To create the final table that we were looking for that will provide a patent number and the number of patents that are co-cited with it 5 or more times, that will just take a final for each loop in Pig to go through the last table that we made and use the filter functionality to filter by the number of the count attribute. In this case, as you can see in the example, we're looking for a greater than 5 value. We will generate this new list with a group attribute and a similar attribute, which will give us what we were looking for. So here are all the queries that we used in this example, just line by line for you guys to take a look at if you want it all easily referenced on 1 page or 2 pages. That was it. Thank you.